The purpose of this video is to show you guys what I'm thinking about the answer key for worksheet 1. So you have the answer key in front of you that I posted earlier, but this is a video to show you what I'm thinking, why I'm thinking the way that I'm thinking, and having more of a verbal explanation in case you don't understand something that I wrote in the answer key. So let's get started. This is question 1. Essentially, question 1 is just graph the data. So we are graphing a position time graph, and that we see immediately that it is no longer linear. So this worksheet is to help you figure out what to do if you have data that is not linear for a position time graph, and how to get a velocity time graph. That is basically the end goal of this whole thing. So let's go through the questions as quickly and as efficiently as we can. So starting with number 2 now, what is the significance of the slope of the position time graph? Well, any position time graph, if you find the slope, whether it's changing or it's constant, you find the velocity of that object. If it is a straight line, like the last test, then the velocity is constant, but in this case what we were doing is we were finding velocities at different points. So in general, the slope of this graph, or any position time graph, is the velocity. Question 3, what is happening to the slope as time goes on? Now, you can pretty much tell how this is working here. If you look, you can see that as time is going on, let's say we have a slope there, and then a slope there, then a slope here, and so on, you notice that the slopes at all 3 of those points are all different, and they are all getting larger. So that is implying that the slope is increasing. Okay, so the slope is increasing. Now question 4 is, what does that tell you about the motion? Well, if the slope is increasing, and if the slope is equal to the velocity, then the velocity is increasing, and we define that word as accelerating. So this object is accelerating. Question 5 through 12, I'm going to do this kind of all at once because it's a little repetitive in what we're doing. We're doing the same thing a few times in a row. So we are finding slopes at smaller and smaller intervals. And the first interval is 0 to 6, that you can see by the blue line. And then we find that slope. Then if you did this correctly, then you'll find that it actually equals 30 centimeters per second. If we do it again from 2 to 5 seconds, when you find the slope, it is also 30. And then, big surprise, when we are at 3 seconds and we draw the tangent line in LoggerPro, we also get 30 centimeters per second. So in all 3 methods, we got the slope is equal to 30 centimeters per second. So this should tell us something about how we can find a slope at any particular instant on this line without using calculus, because otherwise you would have to take a derivative, and we're not going to do that. So what we've discovered here is a pattern. So if we want to find the instantaneous slope, in other words the instantaneous velocity, at any point on that line, we can take an average around it, and it'll tell us what it is at the midpoint. So to find an instantaneous velocity of that graph, then we just calculate an average around the point that we're interested in. So here's the example we did. They're all at 3 seconds. So the point we're interested in is 3 seconds. What is the velocity at 3 seconds? So what we can do is calculate the average 1 second to the left and 1 second to the right. Alright, so this is nothing new. This is what I did in my last video that you saw. And so all we're doing is looking at our delta x. We're looking at our delta x and our delta t, our rise over our run. Alright, so when we do this, big surprise, we get 30 centimeters per second. And that is at the midpoint. It is at the midpoint at 3 seconds. So it's important to know we found the velocity at 3 seconds and only at 3. Okay, 13 was, I realize, a little confusing at first, so I will go through this really quick. What we're doing with this little part is our goal is to get velocity and time so that we can make a graph of velocity and time so that we can get our equation. So what we're doing is we're looking at small intervals. And the first interval we're looking at is from 0 to 1 second and 0 centimeters to 5 centimeters. So our delta t is exactly what you think. It's the change in time for that interval, which is 1. Our delta x is our change in position, which is 0 to 5. So that means it's 5. T mid is exactly what you think. It is the time in the middle between 0 and 1 second. So that's 1.5. No, excuse me, 1/2. And our velocity is just the change in x over the change in t. So in this case, it's 5 divided by 1. Our velocity is 5. Now it's important to know, when we're making our rest of our chart here, we have velocities and times on the two right columns all the way over here and here. So these two columns are what we're interested in, and that will give us a graph of velocity and time. So we can plot that and get an equation. That is the ultimate goal with this project right here. So when you complete the rest of that chart, your graph's going to look like this. And notice that when you plot, you're plotting the t mids versus the velocity, not 1 second, 2 second, 3 second. So if you look here, I plotted 1/2 second, 1.5 seconds, 2.5 seconds, then 3.5 seconds, and so on. And when you plot this, you'll realize you get a linear graph. That is good news because it makes getting the equation easy. There's no linearizing. It just follows the form y equals mx plus b, and we replace y and x with velocity and time. Okay, so we're going to do that. So again, it's y equals mx plus b, and all we're doing is substituting in the numbers. So velocity equals 10 centimeters per second times time. 10 is our slope of that graph. All right, so this is going to be important for the rest of this worksheet. All right, we're using this result and another result so that we can actually derive an equation, a general equation we can use. Okay, so 14 is looking at the same data, but it is looking at it in a linearized graph rather than a velocity graph. So we're going to graph x versus t squared. All right, so this is what we're going to do. When you graph x versus t squared, then you are going to get a linear graph. Big surprise. And so our equation, again, just like we've always done, it's y equals mx plus b, replacing y and x with whatever is on the axes. So when we do this, we are going to end up with x equals 5t squared, 5 being our slope. Okay, so 5 being our slope, you should notice that it looks very similar to the other equation that we have. So remember, this is how we're going to figure out what that slope means. So on to number 15. When we look at any velocity time graph, we defined that the slope of that graph is acceleration. So whatever that number ends up being, it's going to be going that much faster every second. So if we had something that was 10 centimeters per second, ooh, that did not work, 10 centimeters per second, then that means every second we're going 10 centimeters per second faster than we were before. Okay, so this is an acceleration. This is what we have defined as acceleration. Now, when we look at our other equation here, what we see is that our two slopes are exactly double or half of each other. So 10 is exactly the acceleration. 5 is half of that number. So that means the slope of our x versus t squared graph is exactly 1/2 of the acceleration, no matter what it ended up being. So we can generalize both these equations into equations that you can use for more than one situation. So a general equation you can use for, say, a word problem or a lab. And this is exactly what we're going to do. So if you notice that they both have the same slope, units, so they're both at least related to acceleration. So they have the same units. That means they're probably about the same variable, or at least half or double or something. In this case, we found that it was half of the actual acceleration. So I'm going to take you through why this is. So for the velocity time graph, you already know it's centimeters per second divided by seconds, and that gives you centimeters per second squared. If you look at the position versus time squared graph, our slope is change in x over change in t squared, and those units are going to end up being centimeters per second squared. So they have the same units. We have verified that they are in fact both in terms of accelerations. So our first equation, if we generalize it to anything that we could plug into equations and word problems, then we can write it like this. This is something you've seen already, and this is velocity equals acceleration times the time. Now we can do the same thing for the other equation that we have of x and t squared. And so if it is our slope here that we said is exactly half the acceleration, then that's exactly what we're going to write, 1/2 a. So that means it's our general equation here is 1/2 at squared. That is the end result. And then our other one, which is nothing new, it is velocity equals acceleration times the time. And then the last question, this is the displacement. The area under any velocity time graph, whether it is a flat line, whether it goes up like this and then goes back down. Excuse me. Let's go back. And whether it goes back down. Let's say our area was like this funky triangle plus a rectangle. All of the area, no matter what the shape is the displacement of that object. And here is one example that you may have remembered from the test that we just did. So here's an example. Let's make a square and make it easy. If our velocity here was 10 meters per second and it traveled for 2 whole seconds, then the math to find out its displacement is simple. It is 10 times 2, which is 20. If we look at our units and how they cancel, it should be 20 meters. If you also notice that when you look at this graph here, the height of that rectangle is 10, and the width is 2. So you're doing the same mathematical operation for both, you're multiplying the 2. But this is another way of looking at where these equations come from. So hopefully this helps. Please watch this video. Or no, you already watched it. Please, if you did not understand something, come back to class with questions about it, or feel free to watch this again if you missed something. Take care, guys.